The date on this, because I always post everything by date, so if you ever want to look back, that's what you do. All right. You've got your ACs, right? So the first one, for Ms. Yosek's grade 12 applied class, the probability of getting a 70 or higher on the design and measurement test is 62%. So that's the probability right there. The probability of getting a 70% or higher on the probability unit is 46%. So the probability of getting a 70 or higher on both of them, on both tests, so the design and measurement as well as probability, is 28.52. Kalia says that these are dependent events, while Emily says that they're independent. Who's correct? Explain, prove with some calculations. Okay, so what you could do is you could try this. Technically, the probability of design and measurement and probability, right? Technically, if they were independent, if those events are independent, then you could technically take the probability of the first one times the probability of the probability of the other test, like separately, and it should add up to what they are both together. So both together, they're supposed to be 0.2852, correct? The probability of design and measurement getting a 70 or higher is 0.62. The probability on that a student has a 70 or higher on probability, a lot of percentages here, so kind of do it on purpose, so you have to like read carefully. So now we want to see if left-hand side is equal to right-hand side. So this is the best way to calculate that. I have my key here, so what am I doing? So you get, when you multiply these two, you actually do get 0.2852. And that matches what you're supposed to get. So if you individually multiply the probabilities, and you get what they both together are given anyways, if this is true, okay, therefore, events are, what are we going to say? Independent. Events are independent because of that. Okay? Note, if left-hand side is not equal to right-hand side, events are dependent. Okay? That means that one event affected the other one, so we can't just go ahead and multiply both of their probabilities and get what they are together. Okay? The first one has influenced the second one in some way. Okay? This is probably good, a good entry for your study sheet. Let me just see here. On page 50, if you go to page 50 in your book, in your notes, right? There's this entry right here. Sorry about, I couldn't find the symbol for and. This is supposed to say and right there on page 50 of your notes. Probability of A and B is probability times A times probability of B. So if you can see that the left-hand side is equal to the right-hand side, then the events are independent. If you're replacing items that are drawn, right, then if the question says that, then obviously these are independent as well. So either one of these gives it away, that they're independent. Okay? So we'll go back to that in a bit, page 50. So let's keep going. In a bag of 80 chips, 2 will be defective. If you draw 2 chips without replacing the first, right? If you don't replace them, so we know right away this is talking, we're in the area of dependent events. Okay? What is the probability that both chips are defective or both chips are not defective? So this is basically saying defective and defective, or not defective and not defective. And again, we're talking probability. I need to stress that. I'll tell you this for the exam. They will mix up the chapters 4 and 5 are kind of like meshed, as well as some of chapter 3. So sometimes they ask you for number of ways, sometimes they ask you for probability, okay? So if it's probability, we need to have like a fraction, right, where we have a bigger denominator. So defective and defective would mean, right, you grab the first one out of 80, and then you're left with just 1 out of 79, okay? That would be defective and defective. Plus, how many are not defective? If 2 out of the 80 are defective, then 78 out of 80 are non-defective, and therefore, if you grab the next one, there's only 77 out of 79. Okay, so the or there, I hope, gave it away that had to be added there. Okay, or plus. So when you multiply them out, you get. Should I continue on I'm going to continue here. That's 2 times 1 is just 2, and 80 times 79 is 6320. Yes. Plus, the other one is bigger, obviously. That's giving you 3004 over 6320. You can add those up. That's 3006 over 60. Did I get that wrong? Sorry, I got that wrong. I looked at the wrong line. This is reduced 3004, but if you keep it, it's 6006, right? Which will give me, hold your horses, Mr. Dirksen. What are you doing there? What are you doing? 78 times 77 is 6006. And this is correct as well. And then we're going to add these two, so that's 6008. Okay? You may have done it differently. You may have reduced it right away. That's fine. And this stays 6320. If you reduce that, if you leave it like that, you're fine. If you got it as a decimal, is it 0.95 exactly? I don't have my other calculator right now, so sorry. 0.9506 or 95.06%. Okay, so you had to consider both defective, both not defective. And you know what? If it says this right here where my pencil is without replacing, you know that it's going to be something like this, right? Two events that are happening and something is changing. Sometimes just the total, sometimes it's just the total, sometimes it's the top number as well. If you remember to set your alarm clock, there's an 82% chance that you will be on time. If you forget, there's a 25% chance you'll be on time. Suppose you remember to set your alarm 75% of the time. Draw a tree diagram to show all probabilities. So obviously setting the alarm, okay, setting the alarm and not setting the alarm is the first part here. And you remember to set it 0.75% or 75, which is 75%. This is 0.75 right there. And then something happens with you being on time. Okay, time, not on time, being on time, not being on time. Okay, so I'll just say A stands for set alarm. T is for stands for on time. Okay, just a little blurb there. If you set it, then there's an 82% chance that you will be on time. So this is 0.18. If you don't, then there's a 0.25%. Not percent, sorry, should stop saying 0.25%. Just 25% chance of being on time, therefore 75% chance of being late. Okay, I will give you 1 mark for the first, another mark for having these all correct, and then I want you to have the corresponding probabilities combined. Technically, what you're saying when you do the first one, you don't have to have this part. I just need you to understand. You're finding probability of setting your alarm and being on time, which is 0.75 times 0.82. Okay, So I will just give you those, I calculated them already, so this is 0.615, 0.135. I need water. Um, 0.0625, 0.175. I'll give you another mark for that. So this is just out of 3. Out of 3 in total, okay? What's the probability that you will be on time as a percent to 2 decimal places? Being on time, we've got it right here. It's this one right here and this one right here. So we got to add those two. It's probably a really good idea to show which ones you're adding. Just in case you made a mistake up there, we can still see that you know what needs to be done. That's 0.6775 or 67.75%. Okay, if you did that correctly, you get a mark for that. What's the probability that you remember to set your alarm clock given that you're not on time? This one is a tough one, right? Try to translate that. Probability that you set your alarm given that you were not on time. Give me 1 second, guys. I don't know what's happening. It's okay. So this is what it's asking for. So how do we do this again? I have to relate these two here. Alarm and not on time, okay, is going to be, this happened first, right? Yeah, we're going to put this first, not on time. And then it's PA. Let me reread this. What's the probability you remember to set the alarm clock given that you were not on time? Yeah. So this is how you rewrite this. You put this one first, okay, because that's technically happening first within this context. So A and not T, you got to get it from up here. A and not on time is this one right here. So you just replace that. Probability of not being on time, you got to get this branch right here, this one, and this one. So both of these get added up. So I actually show that here. 0.135 plus 0.1875. And I will just call, sorry, we got this. It's supposed to be not T, right? This part is right here. I'm just going to replace that with X. That's totally fine to do that. So you end up with 1.35, and when you add these two up, you get 0.3225x. Can you see that still? I hope so. So we divide both sides by 0.3225. 0.3225. Okay? Cancel that out. And x ends up being 0.4186, which is 41.86%. This one I will give you 2 marks for. Okay? So I will basically give you a mark if I see you setting it up like this. I will already give you a mark, because that to me is important, that you realize that this is what's happening. You're translating this statement into notation. And then I'll give you another mark for actually calculating and getting everything right. Okay? So obviously this number will be different if your tree is off, but other than that, we'll keep it at that. So how much do we have on this page? 2 and 1, that's 3, and another 3, that's 6. Another 2 is 8. Another 2 is 10. So So give yourselves a mark there according to what you did. Remember, ACs are there for you to learn. Overall, if you don't do so well, as long as you're learning from it, it's still going to help you in the long run. Okay, that's what we're after. Here we go. The coin is tossed 3 times. Find the probability of getting at least 2 heads. I don't know how you do this one. I would say tree diagram, in my opinion. Like I always like to come up with some sort of outcome table. I have a lot of fancy ways of doing this, guys, but I'm not going to show you that because then we've got to go and look at like Pascal triangles and all those things. So I'm just going to say, because it doesn't happen very often, we're just going to say 3 times you're tossing it, right? At least 2 heads. So it's a little harder than just going total -1, right? If it's at least 1, then that's the approach I take. But if it's at least 2 heads, then it's a little bit more complicated. So we've got let's go heads, tails, heads, tails, heads, tails. And so this is a little tedious, I know. And you got to be careful. So you got heads, tails, heads, tails. So to me, this is not a 1-mark question. This is a 2-mark question, okay? And the province would do the same. So the first one, it's all 3 land on heads, and then you've got heads, heads, and tail. Then it's heads, tails, heads. Heads, tail, tail. So you got to be careful. And then we go down tail, heads, heads. And then it's tail, heads, tail. Tail, tail, heads, and all tails. I hope you can see that. Let me zoom into that a little bit. So you should have, the first thing you should be able to do is to figure out that there should be 8 outcomes, right? 2 times 2 times 2 is 8 outcomes. This goes back to chapter 4, right? And so count 1, 2, 3, 4, 5, 6, 7, 8. Yes. So at least 2 heads means 2 or more. Okay, you need to be able to translate that, 2 or more. So you have this one, this one, this one. This one doesn't pass. This one is good. No, 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 right? So you've got 1, 2, 3, 4. It's asking for probability. So your NA is what this is, right? So you've got 4 out of the 8 total. So this is NA over NU, okay? So it's 4 over 8, which is half, right? Or 0.5. There you go. Next, 2 cards are drawn from the top of a well-shuffled deck. What's the probability that they're both black aces? I need you to understand that if it's saying this, it's saying one after the other. Okay, one after the other. So we're looking at dependent events here. So you want both of them to be black aces. So you've got 2 black aces out of 52 for the first card, and then now you're down to 1, and it's 51, like that. So that is 2 times 1 is 2. 52 times 51 is 2652. And you're basically done there, right? Or, watch this. I don't know if some of you caught this. You could do, out of 2, we choose 2 black, we want 2 right in a row, and then at the in the denominators, out of the 52, we choose 2 cards. This will give you 1 over 1326, which, if you do the math, is still 0.08%. This is also 0.08%. But I would caution against choosing or using combinations. I would just stick with this method because it's dependent events. This works very well. Okay, so remember that. A die is thrown twice. That's very important there. What's the probability that both numbers are prime? What are our prime numbers again? 2, 3, 5. Right? It keeps going 7, 11, and so forth. But within our die, we're assuming 1 to 6. So these are the only ones that are acceptable. So there are 3 out of 6 for the first roll, and nothing changes, right? You can't remove from a die, and it doesn't affect the outcome of the other. So this is just 9 over 36, right? Or 1/4, if you like to reduce. So 1 mark for that one. The bag contains 5 red, 4 green, 1 blue. That is a total of 10, right? A marble is chosen at random and not replaced. There it is again. A second marble is then chosen. What's the probability that neither is blue? You don't want either one of them to be blue. So you've got 10, right? And so how many blues do you have? 1 is blue, so that means that 9 out of 10 would not be blue for the first one. And then it would be 8 out of 9 for the second one. Okay, because this is assuming that 1 has been removed. And so that gives you 72 over 90, okay, which reduced is 4 over 5, which is 0.8, which is 80%. If you could stop right here and you'd be fine, okay? You don't get any marks for reducing on the exam, and on the test you won't get any either. A code consists of 2-digit number chosen from 00 to 99, followed by 2 different letters of the alphabet. What's the probability that the code would be 12KY? Here's where NA is just this one right here. It's basically 1. There's only 1. They give you all the entries, so there's only 1 option for that. And you have 1, 2, 3, 4. It doesn't tell us whether or not we can repeat, so we're assuming repetition is all right. So we've got 10 times 10, and you've got 26 times 26. Oh, sorry. That's why I read it one more time. 2 different letters. 2-digit numbers chosen from 0 to 99, followed by 2 different letters. So the letters have to be different, right? Yeah. There you go. Almost fell for it. 10 squared times 26 times 25. What is that? 650? So times 100, it's 6500 there. So that's NU. So the probability, because it asks for probability, is 1 over 65,000. There we go. All right, for each of the above, state whether the event involves would be dependent or independent. Question 3. That one was the question 3 was dependent. Okay, setting the alarm affects whether or not you're going to be on time. I think you can wrap your head around that. Question 4, that is independent. Coins and dice are independent. Question 5, 2 cards are drawn. That would be dependent, because you're assuming one after the other. Question 6, that one is independent. The dice again, right? Independent. So you get half a mark for each of these, so you got 2 marks there for that. So 2, 3, 4, 5, 6, 7, 8, because I made 4 out of 2, right? So the back is worth 8 marks. And the front is 10. So this thing is out of 18. Make sure your name and last name is on there. Today's date, the 26th, March 26th.